Okay, number 2, there's a boy that's walking and he changes directions a couple times. Okay, so when we are trying to find a total displacement and it involves more than one dimension, we have to split each separate motion um, into its components. Okay, so the first one is pretty nice because it only has one component. It says that this person, the boy, walks 1.5 kilometers north. So that's 1.5 kilometers, and it's all north. Right, but then there's another motion, 2.8 kilometers at an angle 30 degrees east of north. East of north. All right, so draw the second one, the second thing that said draw it first, north. But we don't go straight north, we go a little bit east. Okay, so think of it um, as you turning. You're pointing north, and then you want to go to the east of north. Okay, so you turn your body, and when you rotate, you have this new direction where you're pointed a little bit northeast. And it tells us that that angle in there is 30 degrees, and that the magnitude of this walk is 2.8 kilometers. Okay, so of that 2.8 kilometers, he changed his direction north, some portion north, but also changed his position east and west. Okay. Generally, when we talk about cardinal directions, you got east, you got north, and we would call both of those the positive direction. And this one, since we graph things on XY planes, we usually think of east and west as the x direction, y and as the north and south direction. So this is a change in his y position. This is also a change in y position for the second movement. And I'll do this one in green. That's a change in his x position. And there's one more motion. 7.5 kilometers at an angle 15 degrees west of north. West of north. Okay, so not quite north. We're going to draw that one first, though. He goes 15 degrees towards the west. Okay, so from the tip of this first vector, we're going to draw our second one that points west, and the resultant is from the beginning of the first one to the end of that second vector. All right, so he's going that way. There's a little zigging and zagging going. So he starts going straight north, turns a little bit east, and then turns back and goes a little bit west. And we need to know the total result of that. This is 15 degrees. 15 degrees. This is 7.5 kilometers. And this is a change in his y position, which is also north and south. And this is a change in the x position. All right, let's do all the y's first. So for the second motion, we've already got the first one done. It's only one dimension. We don't have to split it. It's already split. The second one, we have the y direction is adjacent to this angle, right next to it. Okay, and adjacent divided by the hypotenuse is equal to cosine of theta. So cosine of the angle, 30 degrees, is equal to change in y2 over 2.8. To solve that, you just multiply by 2.8 on both sides, which cancels it out on the right, and just leaves you with 2.8 cosine of 30, which I got 2.4 kilometers, and that is towards the north. Okay. 2.4 towards the north, 1.5 towards the north, and let's also do this last one, the y, change in y. Okay. Again, the y direction is adjacent to the angle, so we're going to deal with cosine again. It's equal to change in y3 over 7.5. So of this 7.5, or wait, what am I doing? As a result of that 7.5 kilometers, we want to know how much, oh dear, we want to know how much our position changed from the y standpoint, the north direction. 7.5 cosine of 15 is 7.2 kilometers north. All right, all that's left is we have to do some x components. So from this first one, well, I guess it's the second one. The first one with an x component, we're going to use sine of 30 is equal to change in x2 over 2.8. 2.8 sine of 30 is equal to the change in his x position from this motion. So we've got, this is going to be not 2, it's going to be 1.4 kilometers. And if you read the question again, it says 2.8 kilometers at an angle 30 degrees east of north. So that 1.4 kilometers is east. Okay, and the last one, again, we're going to use sine because we're looking at the opposite side from the angle. So sine of 50 is equal to change in x3 over 7.5. 7.5 sine of 15 is equal to x. Change in x. And 7.5 sine of 15 is 1.9 kilometers. And that direction is west of north, so this would be west. Okay, I'm going to try to do a dual page thing here. We'll see how this goes. Okay, so we want to add some vectors. I'm going to add the x vectors over here, and then I'll look at the y ones. Okay, so we have some motion that goes to the east. Okay, that's the positive direction, and it's 1.4. And then we have some motion back to the west, and it's a 1.9. So if you recall, when we did some one-dimensional problems like this, we had 1.4, but then we had this 1.9 in the opposite direction. When you add those up, this is a positive 1.4. This 1.9 is in the negative direction. And so you get 0.5 kilometers, and it's negative. Okay? In physics, that negative sign, what that's telling us is not like a negative thing. It's saying that we said the positive direction was east, so a negative number represents 0.5 kilometers west. And that is the total displacement in the x direction. And I'm going to do the same thing for the y direction. And draw some vectors here. Maybe. So we've got 1.5 kilometers north, and then we've got 2.4 kilometers north, and then we have 7.2 kilometers north. Okay? They're all in the same direction, so we just have to add those up, and when you do, you get 11.1 kilometers. Change in y total is equal to 11.1 kilometers, and it's all north. All right, so the last step, we have done all the hard work of taking our vectors, breaking them down into the components so that we can add them up. And now we're going to, once we've added them up, we can put them back together again. That was more of a Humpty Dumpty reference than I thought it would be. Okay, so I'm going to keep the blue line. That is the northward movement. But then we also move a little bit east. And this line right here represents the boy's displacement. Okay, so if you walked, if not the boy, but you walked that green line, you would end up in the same place that the boy did, but instead of having to walk, he walked 1.5 kilometers, then 2.8, then 7.5 to make a total of 11.8 kilometers. Let's see how far we would have to walk if we just wanted to walk straight towards his final destination. And also, if we were going to walk straight towards that final destination, what angle should we walk west of north? Okay, so the reason I drew this line towards the left was because that's west. The blue line goes up because it's north. And we know this one is 11.1. We know this is 0.5. So I'm going to do the Pythagorean theorem. 11.1 squared plus 0.5 squared equals that distance squared. And I kept a lot of decimals when I did this in my calculator. What I got was 11.2 kilometers. Okay. I think you walked 11.8. You only have to walk 11.2 because you didn't zig or zag. You just walked straight there. All right, now that is a distance that he has walked. It is not his displacement because it's not a vector yet. It doesn't have any direction. We don't know theta. So how do we find theta? Okay. Again, we know opposite, we know adjacent, so we're going to use the tangent inverse function. 0.5 over 11.1. And when you do that, you get 2.8 degrees. And what is the direction of that? Okay, so if you, instead of going straight north, we have turned a little bit in which direction? The westward direction. So this is west of north. So somebody says, hey, you need to go meet that boy out there. Say, okay, how far do I have to walk? 11.2 kilometers. Okay, which direction? 2.8 degrees west of north. So you turn north, change your angle 2.8 degrees towards the west, start walking. And that's number 2.